Hello everyone, welcome to our routing and switching class. Today we're going to be talking about module number 5 and we will be discussing about the spanning tree protocol. In this module we're going to be talking about the following main topics. So we're basically going to explain about the purpose of the spanning tree protocol. We're going to talk about the operation of the spanning tree protocol, how it works, and we're also going to be discussing about the evolution of the spanning tree protocol. First topic of the night, we're going to be discussing about the purpose of the spanning tree protocol, also known as the STP protocol. Now, the main focus of this topic is to talk about the causes of loops in a layer 2 network. We're briefly going to explain how spanning tree protocol works and how it addresses the issues that come up with the layer 2 redundant links. The spanning tree protocol is a loop prevention network protocol that allows us to have redundancy while creating a loop-free layer 2 topology. So basically, whenever we want to create a layer 2 topology with redundant links, the most obvious solution would be to have multiple links connecting multiple switches. Now, spanning tree protocol will allows us to prevent loops that are caused by creating redundant links between different switches. Now, STP logically blocks physical loops in a layer 2 network, preventing frames from circling the network forever. So the main purpose of the spanning tree protocol is to make one of the links that is redundant block for a certain amount of time while the other links are working. And this is the way that STP basically prevents frames from entering the spanning tree topology and just basically circling around between the switches forever. Now, spanning tree protocol also compensates for a failure in the network by basically recalculating and opening up previously blocked ports. So just like I said before, and as I mentioned already, when you have redundant links, one issue that redundant links causes to the network is that just basically frames can be navigating through your network forever um, due to a loop being created. Now, spanning tree protocol will help us address this issue. Spanning tree protocol will just basically create a link that is going to be blocking for a certain amount of time. Now, these link can be uh, brought back to life again once there is an issue with the link that was functioning. Now, path redundancy provides multiple network services by eliminating the possibility of a single point of failure. Now, when multiple paths exist between two devices on an Ethernet network and there is no spanning tree implementation on the switches, a layer 2 loop occurs. Like mentioned previously, a layer 2 loop can result in a MAC address instability, link saturation, and high CPU utilization on switches and end devices, resulting in the network becoming unstable. So basically, whenever we have layer 2 loops, it may sound like a great idea. It is actually not that of a good idea if we have no means in preventing the loops and also preventing the MAC address database instability. Layer 2 Ethernet does not include a mechanism to recognize and eliminate endlessly looping frames. So when we talk about layer 3, this is not an issue because layer 3 has the TTL, or the time to live. And as we already know, the TTL just basically decrements every time the packet passes through a router. Now, when we talk about layer 2 topologies, there is no router, so basically there is no hop. And that basically means that a frame can be endlessly traveling through the spanning tree loop. Now, without STP enabled, these layer 2 loops that we just mentioned, they can be formed and they can cause broadcast, multicast, and unknown unicast frames to loop endlessly. And of course, this is terrible for the network. This can obviously bring down a network quickly. When a loop occurs, the MAC address table on a switch will constantly change with the updates from the broadcast frames, which results in a MAC database instability. This can cause high CPU utilization, which makes the switch unable to forward frames. Now, this MAC database instability is related to the way that the switches learn about the MAC addresses. If you recall from Introduction to Networks, the way that the switches learn about the MAC addresses. They just basically learn the MAC addresses by analyzing the source MAC address on every single one of the frames. So once a frame with a certain source MAC address comes from, let's say, port 01, fast Ethernet 01, the switch will basically just register in the MAC table that fast Ethernet 01 is related to this specific MAC address that was in the source of the frame. Now, an unknown unicast frame is when the switch does not have the destination MAC address in the MAC table and must forward the frame out of all ports. Now, this is just basically when there's no entry in the MAC table, and this just comes down to the behavior of the switch. Whenever the switch doesn't know where to send the frame to, the switch will just basically send it everywhere except the port that it came from. This is also known as the unknown unicast frame. Now, a broadcast storm is an abnormally high number of broadcasts overwhelming the network during a specific amount of time. As you may be thinking, this is a terrible situation for the entire network. It just basically means you have too many frames navigating through your network, frames that are not even going to the right destination. Now, layer 2 broadcasts in the network, such as ARP requests, are very common due to the nature of ARP protocol. Layer 2 multicasts are typically forwarded the same way as broadcast by the switch. IPv6 packets are never forwarded as a layer 2 broadcast. ICMPv6 neighbor discovery uses layer 2 multicasts. Now, a host caught in a layer 2 loop is not accessible to other hosts on the network. Additionally, due to the constant changes in its MAC address table, the switch does not know out of which port to forward unicast frames. Now let's talk about how the STP works. Now STP is based on an algorithm invented by Radia Perlman while working for the Digital Equipment Corporation, and it was published in 1985 on a paper. The spanning tree algorithm STA, which is also known as, creates a loop-free topology by selecting a single root bridge where all other switches determine a single least cost path. Now, every time you think about this term, the root bridge, I'd like to think it as uh, the ruler of the spanning tree domain. So just basically the reference for all the other switches. Now, the STP prevent loops from occurring by configuring a loop-free path through the network using a strategically placed blocking state port. So just like I mentioned before, once the STA works, once the spanning tree algorithm takes place, one of the switches is elected the root bridge, also known as the master of all the switches. The switch running STP are able to compensate for failures by dynamically unblocking the previously blocked ports and allowing traffic to traverse the alternate paths. Now, how does the STA create a loop-free topology? So first step is we select a root bridge, which is just basically going to be the reference point for the entire network to build a spanning tree around. We then proceed to blocking redundant paths. Now, spanning tree protocol ensures that there's only one logical path between all destinations on the network by just basically intentionally blocking redundant paths that could cause a loop. When a port is blocked, user data is prevented from entering or leaving that port. Now, the spanning tree algorithm is also responsible for creating a loop-free topology. Now, when we talk about a block port, the effect of having a block port is that just basically all the links are forwarding at a certain time. Now, when there's an issue with one of the links that was operational or forwarding, the STA can just basically recalculate everything and just basically bring a port which was blocking to forwarding state. All right, let's detail a little bit more about the spanning tree protocol operation. Now, just like mentioned before, there are a few steps for STA. STP builds a loop-free topology in 4 steps. The first step is by electing the root bridge. Second step, electing the root ports. Third step, electing the designated ports. And last but not the least, elect an alternate block port. During the STA and STP functions, switches use something called the bridge protocol data units to share information about themselves and their connections. Now, obviously, if we talk about the STA and STP and how they work, there has to be a way for the switches to talk to themselves and just basically discuss, or in other words, elect which one of the switches will be the most important switch in the topology, which is just basically going to be this switch called the root bridge. Now, they exchange this message type called the bridge protocol data units, and they just basically allow them to share information about their connections and to share information about priority and many other things that we're going to see in a few minutes. Now, each BPDU contains a bridge ID, which is one of the most important things. It just basically identifies which switch send the BPDU. The bridge ID is involved in making many of the STA decisions, including root bridge and port roles. The bridge ID contains a priority value, the MAC address of the switch, and an extended system ID. The lowest bridge ID value is determined by the combination of these three fields. So basically, when the election occurs to elect who's going to be the root bridge, the bridge ID is the most important factor that is taken into consideration, and that is just basically because the switch that contains the lowest bridge ID will become what is known as the root bridge. Now, these bridge IDs composed of three fields, like we already discussed. The first of them is the bridge priority, which is just basically a value, a number, uh, which by default is 32,768. It is in a range of 0 to 61,440, and it just basically in increments of 4,096. So that basically means that we cannot assign any value which is not an increment of 4096. In other words, any value that is not a multiple of 4096 cannot be assigned as a bridge priority on a switch. Now, the extended system ID is just basically a decimal value added to the bridge priority value, and it's just basically there to identify the VLAN for the specific BPDU. Now there's also the MAC address. So when we basically have two switches configured with the same priority, the same extended system ID, the switch having the MAC address with the lowest value, which is expressed in hexadecimal, we have the lower bridge ID. So just basically, if everything is a tie, if the bridge priority is the same, if the extended system ID is the same between two switches, the MAC address is there just basically to untie and to make the lowest MAC address the preferred. Now, the spanning tree algorithm designates a single switch as the root bridge and uses it as the reference point for all the path calculations. Now, switches exchange BPDUs to build the loop-free topology, beginning with the selecting the root bridge. So, as mentioned before, determining who's going to be the root bridge is the main step for the STA. Determining who's going to be the root bridge is the reference point for determining who is going to be blocking, who is going to be forwarding, and so on. Now, all the switches in the broadcast domain participate in the election process. That just basically means all of them will talk to themselves. After a switch boots, it begins to send out BPDU frames every 2 seconds. So every 2 seconds, a switch will try to talk to all the switches, and these BPDU frames contain the BID of the sending switch and the BID of the root bridge. Now, the BID of the root bridge is also known as the root ID. Now, the switch with the lowest BID will become the root bridge. At first, all switches declare themselves as the root bridge with their own bridge ID set as the root ID. Now, eventually, after all the switches they talk to themselves, they will realize it's not the case. If they don't have the lowest bridge ID, they cannot be the root bridge, and they will just basically know that there is someone else with the lowest bridge ID which deserves to be the root bridge in the case. Now, in the scenario that is given here, in the scenario that is shown, we have basically a three switch topology. So we have S1, S2, and S3. In this case, S1 was elected the root bridge just because it has the lowest priority out of all of the others. Now, obviously, if there was a tie here between all these three switches, if all these three switches, they had the default priority, for example, 32768, and because we're talking about VLAN 1, it's 32769. If they all had the same exact default priority, S2 would be elected the root bridge, and that's solely because S2 will be the switch with the lowest MAC address. Now let's talk about how to determine the root path cost. Now when the root bridge has been elected for a given spanning tree instance, the SDA starts determining the best path to the root bridge from all the destinations in the broadcast domain. The path information, known as the internal root path cost, is determined by the sum of all the individual ports costs along the path from the switch to the root bridge. Now, when a switch receives the BPDU, it adds the ingress port of the segment to determine its internal root path cost. The default port costs are defined by the speed at which the port operates. The table that is shown in the picture uh, also shows the other path costs for every single one of the different link speeds. Now, the default 1 gigabit per second link speeds is defined by a cost of 4 for the spanning tree protocol standard 802.1d, which was the original spanning tree protocol standard. Now, although all the switch ports have a default port cost associated with them, this port cost is configurable. So that basically means we can change the port cost to a value that we want. So we can just basically manipulate these values to make a certain link or a certain path preferred based on how we want to create the actual forwarding topology. Now let's talk a little bit more about the elect the root ports. Now, once we elect the root bridge, which is just basically the reference point for everything else, we need to elect the root ports. Now, usually the root ports are the ports with the lowest cost that just basically directs to the root bridge. Now, in this case, here is a pretty easy case because we have all the links as fast Ethernet links, and that just basically means they all have the same exact cost. So, for example, for S2, we have the cost to S1. Now we can take two paths. Now, because every single one of the trunks, they have the same speed, they have the same cost. Now we just basically have to add the cost for every single one of the links until we reach the root bridge. Now, once we are checking which path is the best path for S2 to reach the root bridge, we come down to path 2 and path 1. Obviously, path 1 is just one link, so it's just basically taking the trunk number 1. Now, the other way that switch 2 can reach switch 1 would be going through the second path. That would just basically require S2 to send the frame to S3 before it sends to S1. So that just basically means if it chooses path 2, we will have to go uh, to trunk 2 and then trunk 3, and that would mean the cost will be a little bit higher. Now, every segment between switches will have one designated port. The designated port, just like mentioned, is the port which goes to the root bridge with the lowest cost. The designated port is a port that has the internal root path cost to the root bridge. In other words, the designated port has the best path to receive traffic leading to the root bridge. Now, what is not a root port or a designated port becomes an alternate or blocked port. So once we determine who's going to be the designated ports, who's going to be the root ports, and remember the way we determine the root ports? Just basically by checking who has the lowest cost to the root bridge. After we determine the root ports, all the ports in the root bridge itself that leads to root ports, they are called the designated ports. Now, once we determine all the designated ports, once we determine all the root ports, we can just proceed to determining the designated ports. The blocking ports. Now, if a port is not a root bridge or a designated port, then it becomes an alternate or backup port. Alternate ports are in discarding or blocking state to prevent loops. In the picture that is shown in the scenario that we're basically studying, we have the root bridge, which is elected to be S1. S1 has all the ports as designated ports, and S2 and S3, because all the links, they have the same bandwidth, the same speed. We have S2 Fast Ethernet 01 being the root port, and S3 Fast Ethernet 01 being another root port. And because of that, we have to find who of switch 2 or switch 3 Fast Ethernet 02 will be the port in alternate port. Now, the way that we do this is just basically by verifying And the way we do this is just basically by verifying the bridge ID one more time. We just basically compare the bridge ID between S2 and S3. If S2, which in this case has the lowest bridge ID, S2 will actually be the one with the designated port. Now, when a switch has multiple equal cross paths to the root bridge, the switch will determine a port using the following criteria: lowest sender bridge ID, lowest sender port priority, and lowest sender port ID. Now, lowest sender bridge ID, another topology just like the one we studied. We have a topology with 4 switches, with switch 1 as a root bridge, port F01 on switch 3 has a port F03 on switch 4, have been selected as root ports because they have the root path calls to the root bridge for their respective switches. Now S2 has 2 ports, Fast Ethernet 01 and Fast Ethernet 02. They all have equal cross paths to the root bridge. The bridge ID of S3 and S4 will be used to break the tie. This is known as the sender's bridge ID. S3 has a bridge ID of 32769 all fives, and S4 has a bridge ID of 32769 all ones. Because S4 has a lower bridge ID, the fast port Ethernet 01 port of switch 2, which is the port connected to switch 4, will be the root port. Now, once determined who's going to be the root port, we can then basically determine the rest. Now, another way of electing the root port from multiple equal cost paths is with the lowest sender port priority. The topology shown below has 2 switches which are connected with 2 equal cost paths between them. S1 is the root bridge, so both of its ports are designated ports. S4 has 2 ports with equal cost paths to the root bridge. Because both ports are connected to the same switch, the sender's bridge ID is equal. So the first step is a tie. Next, the sender's S1 port priority. The default port priority is 128. So both ports on S1 have the same port priority. So this means there's another tie. We need to find another way to determine who's going to be the designated port. Now, if either port on S1 was configured with a lower port priority, S4 would put its adjacent port in forwarding state. The other port on S4 would be a blocking state. Now, lowest sender port ID, the last tie breaking the lowest sender's port ID. Switch 4 has a receive BPDU from port F01 and port F02 on switch 1. The decision is based on the sender's port ID, not the receiver's port ID. Now, because the port ID of F01 on switch 1 is lower than the port F02, the port on F06 on switch 4 will be the root port. This is the port on S4 that is connected to the F01 port on S1. Port F05 on S4 will become an alternate port and placed in the blocking state. Now, STP convergence requires 3 timers. We have the hello timer. The hello timer is the interval between the BPDUs, so every time the switches talk to themselves. The default is 2 seconds, but that value can be modified between 1 and 10 seconds. Forward delay timer. The forward delay is the time that is spent in the listening and learning state. The default is 15 seconds, but that can also be modified between 4 and 30 seconds. Now, the max age timer is the maximum length of time that a switch waits before attempting to change the STP topology. The default is 20 seconds, but that can be modified to between 6 and 40 seconds. The default times can be changed on the root bridge, which dictates the value of these timers for the entire STP domain. STP facilitates the logical loop-free path throughout the broadcast domain. The spanning tree is determined through the information learned by the exchange of the BPDU frames between the interconnected switches. If a switch port transitions directly from the blocking state to the forwarding state without information about the full topology during the transition, the port can temporarily create a data loop. For this reason, STP has 5 port states, 4 of which are operational port states, as shown, and the disabled state is considered non-operational. So these are all the states that the ports they can have in a spanning tree protocol. Now, this is everything that happens in every single one of the states. When we have a port in the blocking state, it is only allowed to receive BPDUs only. The MAC address table does not update, and the forwarding data frames does not occur. Now, for the listening state, we just basically have a state that allows the port to receive and also send BPDUs. However, there is no MAC address table updates, and the port is not allowed to forward any of the frames. When we talk about the learning state is a state that allows the port to receive and send BPDUs and also update the MAC address table. Now, the only thing that the learning state port cannot do is forward frames. Now, the forwarding state is the state that we desire to have. It's just basically a state that allows the port to receive and send BPDUs, update the table, the MAC table, and forward the frames. We also have the disable port, which is just basically a state that does not allow the port to send or receive BPDUs. It doesn't allow the port to do any MAC address table updates and nor even forward the frames. It's just basically a state which is determined to be behaving exactly the same way as a blocking state port. Now, STP can be configured to operate in an environment with multiple VLANs. Now, once we have an environment with a single VLAN, the drawback of having an environment with a single VLAN running STP is that one of the ports, one of the links will be blocking at all times. So it's usually a topology where you're going to see links that are green, links that are orange. The orange links will be the links that are blocking temporarily, and so on. Now, STP can be configured for environments with multiple VLANs, and when we do this, we're basically doing a per VLAN spanning tree PVST version of STP, and there's a root bridge elected for each spanning tree instance. So for every single VLAN, we're gonna have a spanning tree instance. This makes it possible to have different root bridges for different sets of VLANs. STP operates as a separate instance of STP for each individual VLAN. So a huge advantage of PVST is that we can have blocking ports for certain VLANs, but we can also have different blocking ports for other VLANs. And as a consequence of this, if we have a look at the topology itself, you may see that all the links, all the ports, they are green, they are forwarding, but they are forwarding for specific VLANs. Let's talk about the evolution of STP. Now, many professionals generically use STP to refer to the various implementations of the spanning tree, such as RSTP, MSTP, but they're not exactly the same thing. When we talk about RSTP, MSTP, they're actually different than STP. Now, the latest IEEE documentation on spanning tree says that STP has now been superseded by the Rapid Spanning Tree Protocol. The IEEE uses STP to refer to the original implementation of spanning tree and RSTP to describe the version of spanning tree specified in IEEE 802.1d 2004. Now, because the two protocols share much of the same terminology and methods for the loop-free path, the primary focus will be on the current standard and the Cisco proprietary implementations of STP and RSTP. Now, for Cisco switches running iOS 15 or later, PVST Plus is running by default. This version incorporates many specifications of the IEEE 802.1d 2004, such as the alternate ports in place of the former non-designated ports, and switches must be explicitly configured for rapid spanning tree mode in order to run the rapid spanning tree protocol. Now, these are basically the major differences between the STP varieties, the STP protocols, and their differences. So whenever we talk about the STP itself, the original STP, the original standard, we are just basically talking about a protocol that provides a loop-free topology in a network with redundant links. Now, this is also called the Common Spanning Tree CST, and it assumes one spanning tree instance for the entire bridged network, regardless of the number of the VLANs. So it doesn't matter the VLANs for the original STP. The original STP doesn't even care about the VLANs. It just basically has a single topology for all the VLANs. Now, the PVST Plus, which is just basically the per VLAN spanning tree, is a Cisco enhancement of the STP, and it provides a separate 802.1d, which is the original standard, instance for every single VLAN configured in the network. PVST Plus supports port fast, uplink fast, backbone fast, so a few more features compared to STP. Now, the 802.1d 2004, which is just basically an updated version of STP standard, incorporated by the 802.1w. We also have the RSTP, the Rapid Spanning Tree Protocol, or 802.1w, which is an evolution of the STP that provides much faster convergence compared to STP. And it does that by having different port rows and a few things, and implementing a few things differently. We also have the Rapid PVST Plus when we apply all the RSTP to the PVST Plus and provide separation of instances per VLANs for the 802.1w standard. We also have the MSTP, which is just basically the multiple spanning tree protocol, which is a IEEE standard inspired by the earlier Cisco proprietary multiple instance STP or MISTP. MSTP just basically maps multiple VLANs into the same spanning tree instance. Now, this spanning tree instance is just basically a group of VLANs that we can create. Once we create this group of VLANs, we can assign VLANs to a certain group, and we can just basically have a topology per group instead of per VLAN. Now, the MST, which is the multiple spanning tree, is the Cisco implementation of the MSTP, provides up to 16 instances, and combines many VLANs with the same physical and logical topology into a common RSTP instance. It also provides a few features such as the port fast feature, the BPDU guard, BPDU filter, and so on. Now, the RSTP supersedes the original 802.1d while retaining backwards compatibility. That just basically means if you have a switch running RSTP, another switch running 802.1d, which is the Common Spanning Tree Protocol, the CST standard, it would just basically work because the 802.1w is backwards compatible. Now, most parameters have been left unchanged, and users that are familiar with the original standard can easily configure the RSTP. The same algorithm is used for both of these standards to determine the port rows and the topology. Now, RSTP increases the speed of the recalculation of the spanning tree. When the layer 2 network topology changes, RSTP can achieve much faster convergence in a properly configured network. Sometimes in as little as a few hundred milliseconds. If a port is configured to be an alternate port, it can immediately change to a forwarding state without waiting for the network to converge. Now, Rapid PVST Plus is the Cisco implementation of the RSTP on a per VLAN basis. With Rapid PVST Plus, an independent instance of the RSTP runs for every single VLAN. Now let's compare the port states, the port rows on every single one of these standards. There are only 3 port states in RSTP. They correspond to 3 possible operational states in the original STP. The 802.1d included the port states disabled, blocking, listening, which were merged into one single state called the discarding state in RSTP. The learning and the forwarding states, they just basically remain the same. Now, root ports and designated ports are the same for both STP and RSTP. However, there are 2 RSTP port rows that correspond to the blocking state of STP. In STP, a blocking port is defined as not being the designated or root port. RSTP has 2 port rows for this purpose, which are the backup port and alternate port. The alternate port has an alternate path to the root bridge. The backup port is a backup to share a medium, such as a hub. A backup port is less common because hubs are now considered legacy. Just basically means in one of the most modern topology is one of the most modern networks, we are not likely to see this port state called the backup port. Now, when a device is connected to a switch port or when a switch powers up, the switch port goes through both the listening and learning state each time, waiting for the forward delay timer to expire. This delay is 15 seconds for each state for a total of 30 seconds. This can present a problem for DHCP clients trying to discover the DHCP server because the DHCP process may time out. So basically, once we plug in a certain host machine to a switch port, you guys may have seen this, you may have come across this before, especially into one of our CIT's labs. You connect the computer to one of the switch port, the port will just basically blink amber instead of going green straight away. And it would just basically take a few seconds for the port to become green and to just basically start forwarding. Now, this is caused by the fact that STP is enabled by default on all the ports, and that just basically means there is a delay due to the fact that the spanning tree algorithm is trying to find out the root bridge. Now, obviously, if you have a computer being connected to the switch port, a root bridge will never be elected, and basically trying to elect a root bridge is a pointless process. Now, when a switch port is configured with port fast, we'll just basically prevent this from happening, and that is because the port transitioning is for blocking to forwarding state immediately. And this will just basically avoid the 30-second delay. Now, this is beneficial especially if you have a DHCP environment, you want to plug in a computer and you want the computer straight away to try to find a DHCP server and obtain an IP address. You most likely going to enable port fast on this port, which is going to be connected to an end device. Now, over many years, organizations required greater resilience and availability in the LAN. Ethernet LANs went from a few interconnected switches to a single router to a sophisticated hierarchical design, including access, distribution, and core layer. Now, depending on the implementation, layer 2 may include not only the access layer, but also the distribution or even the core layers. These type of design may include hundreds of switches with hundreds of even thousands of VLANs, as CP has adapted to added redundancy and complexity with enhancements as part of RSTP and MSTP. Now, if we usually have over 1,000 VLANs, over 1,500 and so on, RSTP, PVST, they don't scale very well, and that's why it's a good idea to migrate to MSTP instead. Now, layer 2 routing allows for redundant paths and loops in the topology without blocking ports. For these reasons, some environments are transitioning to layer 3 everywhere except where devices connect to an access layer. Basically, if we have the standard design, we have the access, the distribution, and the core layer, people are usually bringing down the layer 3 into the access layer to avoid having the redundant links. And that's the end of our module number 5.